Good evening, everyone. In our last class, we have been talking about the planar chromatography. Okay, so we discussed about planar chromatography. In the planar chromatography, we saw the matrix or the stationary phase in which we perform the chromatography, that is present as an x and y in the x and y coordinate. Say this is x and y coordinates. So just like in a 2D plane. Okay. However, in the column chromatography, as the name suggests, we have columns. Okay. Now in columns, the columns may be of two types. The first one is packed column. So there will be a column, and within that we will be having the stationary phase, which will be packed inside it. Okay. The second type of column, it is regarded as capillary column. So we'll be having small capillaries, and within that capillary we will be having a thin layer of the stationary phase. Okay. Now this thin layer of the stationary phase, it may be a liquid phase, or it may be the functionalization of the capillary tube itself. Okay. Now in the column chromatography, if you see, this is a chromatographic method which is used to isolate a single chemical compound from a mixture. Okay. We are interested in a single chemical compound from the mixture. Now the separation of the analytes over here, it is based on differential absorption of compounds on the adsorbent, while the compounds, they are moving through the column at different rates, which allows them to get separated in the fraction. So when we talk about the differential adsorption, that means, if you remember in the first case, in the planar chromatography, when we applied some analytes, they were moving faster, and some of them they were moving slower as compared to the other. Okay. Over there, what we were having the partitioning effect. We were having a partitioning effect. Okay. However, in the column chromatography, specifically this packed column chromatography, over here we have differential adsorption. Adsorption, it is a solid, it is a phenomena where the solid substances, they have a specific affinity for a particular analyte. Okay. So herein what we'll be having the adsorbents, and say another analyte A, it may get adsorbed onto the surface of the this stationary phase, whereas the second analyte B, it does not have the affinity for the adsorbent, and accordingly it moves out. Okay. क्या बात है, आप बहुत मुस्कुरा रहे हो? Is there anything special which you want to share with everyone? Yeah. So anyway, just like in our TLC, or the planar chromatography, where we had this normal phase chromatography and a reverse phase chromatography, and the reverse phase chromatography. Here also we have normal phase chromatography and the reverse phase chromatography. Okay, in the normal phase, what we have discussed, in the normal phase, our adsorbent layer or the stationary phase, it is hydrophilic in nature. Okay, whereas in the reverse phase, our stationary phase, it is hydrophobic in nature. Okay, now we have a variety of adsorbents that are available, which can be used along with a wide range of solvents. Okay, and due to this reason, this chromatographic technique, it has been regarded as a versatile technique, and it allows us to separate or purify a large number of analytes. Okay, depending upon what is the shape and the size of your column, you can separate starting from the microgram of your analyte even up to kilograms of the analyte. Okay, in industry you will be finding that there are very large columns which are there, which are quite helpful in separating the analytes, whereas if you want to do the same thing in the laboratory scale, you will be finding that you are having small analytes, small columns, sorry, you will be having small columns. Small columns means the columns may start from say 10 centimeter column, they are also available. Okay, so depending upon what type of where you want to do, you can whether you want it for say for the analysis of something, you can go for a smaller column. If you want to purify a large number of substances, say for example in the industry, then for the purification you may need a larger number of a larger size of the column. Okay, the main advantage of the column chromatography is that it is relatively low cost and you can dispose of the stationary phase. Okay, dispose of the stationary phase. Now, because of this reason, what happens is that this type of column chromatography, it prevents cross contamination, the first important point, since you are after every run you are disposing of the stationary phase. That means what happens is that suppose some a person, he has run some analyte, okay, and after that he has gone, okay, and he has not washed the column properly. Now another person B, he comes and he tries to run his own sample. Now if the column has not been washed properly by the person A, there will be traces of some analytes from the previous experiment which will gain entry into the second experiment, and it will hamper the results. Okay, so they will be, so he will be getting some false results, so that is not acceptable. The second thing is the stationary phase, the degradation. Okay, so what happens, you must have seen the rivers. So suppose these are the coastline of the rivers. Okay, now when the river flows, what happens, with time these coastlines, they degrade. Even though they are solid, they start degrading. The same phenomena happen in the column chromatography. What you have within the columns, you have solid materials which are basically regarded as the stationary phase. Now if you continuously run some mobile phase, what it will do, it will corrode these stationary phases, and what is happening, the degradation of the stationary phase, it is happening. So that is also not proper thing. Okay, the reason being, if it starts to degrade, what will happen, the particle size of the stationary phase, it will decrease, and the packing of those particles within the column, it will be quite denser. Okay, so if it becomes slower, the packing will be much more closer. So there will be a change in the flow rate, flow properties. So your experiments will be hampered, because say if you have performed the experiment for the first time, whatever the result you will be getting, if you perform the same experiment after 10 times, due to the degradation of the stationary phase, the property of the column has changed, and if the property of the column has changed, you will be getting totally different results. Okay, so the use of this column chromatography, it helps you in overcoming these two types of disadvantages which may happen with some other techniques where you are continuously using the columns. Okay, the same column. Now this column chromatography, it can be done either using the gravity. Okay, so what does the gravity does? The gravity helps us for moving the solvent through the column. Okay, and in the second case, we can use compressed gas to push the solvent through the column. Okay, so either you can perform the chromatography under the gravity or by using compressed gas to move the solvent. Okay, now this is a typical column chromatography. So you have an empty column. Okay, so in this empty column, what we do is that a filter paper is being placed over here. Just after the filter paper, a cotton layer, a thin cotton layer, it is being placed. A thin cotton layer, it is being placed. Then we have another layer of the filter paper. Okay, so this is called the packing. So what we are doing, we are basically using this pad. So this is a pad which we are making. So we are using this pad because when we will be pouring the stationary phase, which are basically available as powder, into it, this powder, they don't gain entry into this small channel. If it gets entry into the small channel, it will block the channel. Okay, and then you will not be able to work over there. So after the padding is done, then we add this stationary column and this stationary powder. So this stationary adsorbent, it is added. After that, over this one, another pad, it is being added. Okay, this whole process from the from putting up the lower pad to the addition of the stationary phase, subsequently to the addition of the upper padding, this whole process, it is called the packing of the column. Okay, and the packing of the column is the major what do you call it, it is the main what do you call procedure which will help you in the separation of the analytes. If you are not able to pack the column properly, then your experiments will not be repeatable in nature. Okay, the packing of the column is the main important step while you do the chromatography. Okay, so once you do this, then the solvent layer is added such that you collect some of the solvents beneath it, and whole of your column, it is filled with the solvent. Okay, so this step, it is called solvation. This step is called solvation. Okay, so in this case, what happens is that the column, it keeps hold of the of the solvent within the bed. Okay, now usually this solvent, the solvent with which we do the solvation, it is nothing but your mobile phase, which you will be later on using for the elution of the analytes. Okay, then you keep it for some time so that you have reached to an equilibrium, and if you see the upper the solvent layer, it vanishes out and you get to the your solvent gets to the this thing, and you have a solvated column. Now thereafter you can add the analyte. You can add this analyte over here. Once the analyte is added, then you have the analyte which gets spread over the column. Okay. Now another important thing which I forgot to mention, why you want to do this upper packing. The reason being, suppose you might have seen that from the rooftop, when there is rain, so if you are having some channel like thing, and if some rainwater is falling onto the ground, so what happens? You will find that a crest is formed at that position where the drop of the water is falling. The same thing over here also, when you will be adding the solvent from the top, if you do not give this padding, what will happen? It will affect the packing of the column. Okay. And to avoid this, we add this pad, and this pad, what it does is that it helps in proper distribution of the solvent on the surface of the column. Okay. Now once you have this, then you add solvents, and while you are adding these solvents, you can see the analytes, they are getting separated, and since there is a differential absorption of the different analytes, say the blue one, say it is A, and the second one, red one, is B, because the analytes A and B, they are having differential absorption on the stationary phase, there is a change in the velocity of this solvent of these analytes through the column. Okay, so there is a change in the velocity of the analytes through the column, and due to that differential absorption, this red analyte, it is collected first, and subsequently the blue analyte, it is collected in the second stage. Then if you further continue, all the analytes, it will be collected, and you will be at the later stage, you will be only getting the solvent what you have been adding. Okay, so this is the example or a pictographic representation of a column chromatography. You have the column over here, and if you see on the top, you have a bowl like structure. So this is called the reservoir. Reservoir of what? Reservoir of this the mobile phase. Reservoir of the mobile phase. So you keep the mobile phase over here. So beneath that, you have a stopcock somewhere over here. So from there, you can regulate the flow of the liquid into the column. Okay. Now if you see, initially all the things are quite packed. Now as the time progresses, you can see the yellow band, it is moving further and further, and if you see, there is a separation of these bands over here, and these bands they are being collected during the elution process, and in this way the different chromopores, they can be collected. Okay. Then displacement chromatography. Displacement means you need to displace something. Okay, so what you have, suppose you have a matrix of A. Okay, in the analyte or in the compound or in the in your sample, you have a mixture of, say, C, D and E. Among the C, D and E, you know that D, it has got a special liking for the A. So what it will do, it will go, while you are eluting it, it will go and it will get absorbed onto the A, while the C and the E, they will be moved out of the column. Okay. Now once it is done, so next what, in the column, you know only D is there, then what you do? You add another analyte, say X, which is having more affinity towards the A. So what it will do? It will displace the D from the stationary phase, and that D can be corrected easily. Okay, so this is how a displacement chromatography it works. So a molecule with a high affinity for the chromatography matrix, the displacer competes effectively for the binding sites and thus displaces all molecules with lesser affinities. There are distinct differences between the displacement and the elution chromatography. In the elution mode, substances typically emerge from a column in narrow Gaussian peaks. Wide separation of peaks, preferably to baseline, is desired for maximum purification. The speed at which any component of a mixture travels down the column in elution mode depends on many factors, but for two substances to travel at different speeds and thereby dissolved, there must be substantial differences in some interaction between the biomolecules and the chromatography matrix. Okay. Operating parameters are adjusted to maximize the effect of this difference. In many cases, baseline separation of the peaks can be achieved only with gradient elution and low column loadings. Okay. However, the drawbacks of the elution mode is that there are operational complexity and we get low throughput. Okay. Whereas on the other hand, the displacement chromatography, the components are resolved into consecutive zones of pure substances rather than peaks. A larger column feed can be separated on a given column with the purified components recovered at significantly higher concentrations. Okay. So the elution one, the elution chromatography is over here, where we have seen that there is an elution of the thing. Here, all the analytes, they have some affinity towards the column stationary phase. However, that likeliness is a differential proportion. So there is a differential adsorption of likeliness of the analytes towards the stationary phase. However, in the displacement chromatography, there is only one analyte which will be having a much more or much stronger affinity um, towards the stationary phase, and we have to use a displacer to later on we have to use the displacer to displace the analytes through the column. Okay. Now techniques by physical state of the mobile phase. So over here, first one is the gas chromatography. Now when we call it as gas chromatography, we mean to say, so in the gas chromatography, so what we have, when we talk about this gas chromatography or liquid chromatography, basically we mean the gas is the mobile phase. If we say liquid chromatography, the liquid is the mobile phase. Okay. So in the gas chromatography, we usually have gas liquid chromatography. Okay. Now when we talk about this gas liquid chromatography, in short it is called GLC, and when we call it as gas chromatography, it can be a packed column chromatography. Packed column means just like over here where we have packed the column, here also we can pack the column. Instead of using the solvent over there, we can use a gas as the mobile phase. Okay, then it will become gas chromatography, gas chromatographic system. Okay, so the gas chromatography, it can be a packed column chromatography. On the other hand, it can also be a capillary chromatography. In the capillary chromatography, what happens? You have the capillary, and within this capillary, a solvent layer, it gets adsorbed. Okay, so that liquid which gets adsorbed onto the inner surface of the capillary, that acts as the stationary phase. However, in the packed chromatography, as the name suggests in the gas liquid chromatography, we need a liquid, so there would be the stationary phases which are particulates or powdered in shape. However, these layers, they will be coated with a thin layer of the liquid, okay. Now this liquid, it will help you in the partitioning of the analytes between the gas and the liquid. So in GLC, the packing material or the packing powder, it is coated with a thin layer of the solvent, which acts as the stationary phase, okay. So in general, the preparation of the packed columns, they are very easy, and hence packed column gas chromatography are more commonly used. However, the capillary columns, they give you far superior resolution as compared to the packed columns, okay. However, you can understand capillaries, they will be having very fine tubing like structure. So the preparation of the capillary columns, it is very difficult, and hence its cost is also very high, okay. However, they are quite widely used if you have a very if you have a complex mixture, and you want to extract the analytes from that complex mixture, okay. Both types of column, they are made of non-absorbent and chemically inert materials. So usually the columns, they are made up of either stainless steel or the glass, and are the usual materials for packed columns, whereas quartz or fused silica, they are used for capillary columns, okay. Now this is the schematic diagram of a gas chromatograph. So you have a carrier gas, and then you control the flow of the gas through the flow controller, okay. Now it has the connection to the column. Over here, if you see the column, it is circular in nature. However, in the previous cases, we have seen the columns, they are cylindrical in nature, okay. So these are also cylindrical, but they are arranged in the helical shape. Why? Because we want to increase the length of the column. We want to increase the length of the column, and we want to keep it within a short, in a very small space. Hence, they are converted into a what you call spiral shape, and the gas, it moves through this column, and then we have a sample injector which helps you in injecting the sample into the column, and the gas, the mobile phase which we are using, it comes at this juncture, and then it carries the samples into the column, okay. So we do not have to add the sample over the column. In the previous case, if you see, we had added this, okay, we have added this sample over here, and then we have started adding the mobile phase. However, in this case, in the gas chromatography, the gas is continuously flowing, and then you inject the sample over here, and at the same time, what happens, since the gas is continuously flowing, it takes the complex mixture into the column, okay. Now this column, it is having a controlled temperature, and that temperature control, it is being carried out using the column oven, okay. Now after the separation has taken place, you have this detector. So we can have different types of detectors, okay. Now this detector, you will be having a waste, and this detector, it will find out the concentration, or it will try to analyze the analyte, what type of analyte you are getting, and it will give you the chromatogram over here, okay. Right. So the rest of the thing, it goes as the waste. Okay. The most commonly used detectors are the flame ionization detector, we have already discussed, and the second type of detector is thermal conductivity detector. Thermal conductivity detector also we have discussed. Okay. Now next type is liquid chromatography. So the mobile phase in the liquid chromatography, it is liquid. So liquid chromatography, it generally utilizes very small packing particles, and a relatively high pressure is referred to a high performance liquid chromatography. Okay. So that is regarded as the high performance liquid chromatography. The chromatography, this column chromatography, what we have discussed, it is also a liquid chromatographic technique. However, over here we are discussing it separately, because if we use a high pressure where we can use the gases, compressed gases, to improve the what you call flow of the mobile phase through the system, and through that we can control the flow of the liquids. Since we are able to manipulate the liquid flow or the mobile phase flow through the column, we are able to get very good resolutions. In the previous case, what it was happening, the elution, it was happening only due to the gravity, and over there we did not have any control to modulate the flow of the mobile phase. However, in this case we have a technique to control the flow of the mobile phase by using a pump. The pump may be using a compressed gas, or the pump may be a pulsatile flow, or a continuous type pump may be there, which will be continuously putting a pressure onto the column, so that there is an uniform flow of the liquid throughout the column. Okay. So in HPLC, the sample is forced by a liquid at high pressure through the column. Now HPLC, historically it is divided into two different subclasses. The normal phase liquid chromatography, which is regarded as NPLC, and the second one is reverse phase liquid chromatography, RPLC. We have already talked about what is the nature of the NPLC and of the stationary phase of the NPLC, and what is the nature of the stationary phase in the RPLC. So in NPLC we have toluene. It is just an example, toluene, which is hydrophobic in nature as the mobile phase, and silica as the stationary phase. So silica, it is hydrophilic in nature, and toluene, it is hydrophobic in nature. So in NPLC we have hydrophilic stationary phase and hydrophobic mobile phase. On the contrary, in RPLC we have water methanol mixture in different proportions as the mobile phase, and C18 octadecyl as the stationary phase. So this is the example of an, or the flow diagram of a preparative HPLC apparatus. So there are two sample containers. Okay. So if you see, previously I have told that this water methanol mixture, it may be needed. Okay. Now when we are having this water methanol mixture, the water methanol mixture, it can be, say, in 90 to 10%, say 90% water, 10% ethanol. Then it may also be, say, 50% water, 50% ethanol. So it all depends on what type of mobile phase you may be needing. So in this case, we have the reservoir for both types of the solvents, and now both types of the solvents, it goes, or it is being pumped by these high pressure pumps. There are two pumps, say high pressure pump, this is one and this is the other one. So high pressure pump for the solvent A and high pressure pump for the solvent B. Okay. Now thereafter we have, in both the cases we have this degasser unit. Okay. So what the degasser unit does, degassing means it will remove the gases which are either dissolved within the gas, or it means so happens when you are pumping the solvent, there may be some air bubble which may gain entry over here. So the degassing unit, it removes the gases over here. Okay. So what happens if these gases gain entry into the column? If these gases they gain entry into the column, they may block the column. Okay, they may block the column. So you may have seen, suppose if you have water pump at your home, sometimes what happens, if you put on the pump, what may happen is that if water supply is not there, the pump will suck air, and if the pump sucks air, what it will do, it will not be able to pump water. The same thing happens over here also. If these air they gain entry into the column, it will choke the column and your column will be destroyed. Okay. So what happens is that you get this thing, and then through here, through these valves, they gain entry into a mixer. Over here you are having this mixture. Okay. Now depending upon the control of this, you can control these valves depending upon how you are controlling this valve. The solvent A and the solvent B, they will be mixing in that proportion. Okay. So this valve, it will govern, or it will help you in mixing the different solvents so that you get a proper mixture. Okay. And why do you want this gradation? Because if you have this gradation, if you are having water in higher quantity, the hydrophilicity of your solvent will be higher. If you are having methanol in larger extent, comparatively the hydrophobicity of your solvent will be higher. Okay. So this will affect the partition coefficient of your solids. Okay. Due to this reason, we need to prepare this hydromethanolic or hydroethanolic solvents of different compositions while we are doing the analysis. Now due to this reason, over here this mixer and these valves, they help us in making a mobile phase of definite composition. Okay. They help us in making a mobile phase of definite composition. Okay. So if you are having a definite composition, they will be having a definite hydrophilicity or definite hydrophobicity. Okay. Now once it is there, so this mobile phase, it gains entry over here. So in this case we have this switching valve. Now this switching valve, I am not going into the mechanics of this one. So what it does is that it collects the sample from the this sample injector. Okay. So this is the sample injector over here. So the manipulator, this manipulator, it will have a, what you call it, it will have a capillary, and it will dip this capillary into the different solvents, and then from there the solvent will be sucked into this sample injector. Okay. So this sample manipulator, see, in this case they are having a different type of here. So this robotic arm, it will take it and it will put it over here, just beneath the sample injector. Okay. So it will suck the sample and it will put into this switching device, and at the same time you are also having the this mobile phase coming into the switching valve. So there is a switching mechanism at a particular instance of time. When you want to inject the sample will be this switching device, it will put the this line from the sample injector in flow with the column, and then it will again immediately revert back to its original position, so that it will allow the mobile phase to pass through the column. So in that way, you have inserted the sample into the column, and then consequently you will be having the mobile phase which will be trying to push the analytes or the samples within the column. Okay, then you have these columns, and then this whatever the output from this column you are getting, it goes through the detector. Over here you have this detector, and then the fractions, they are being corrected. Okay, now as I told you, there are two types of sample injecting system. One is like this, where you have a robotic arm. Now this robotic arm, it will take this sample holder and it will bring it over here. Okay, and then it will be injecting. Another thing is that another type of sample injector is there, where you have these bottles which are kept at the same place. Okay, however, in all of this you will be having some capillaries. Now the program will choose from which capillary you want to sample out, and accordingly it will be directing the sample into the this switching device. Okay, so this is the flow diagram of your HPLC apparatus. Then we have ion exchange separation. So we have under this we have ion exchange chromatography. It is similar to the affinity chromatography. However, in this case, what we have, suppose you are having a matrix. Okay, now this matrix, this stationary phase, it is ionized. Say for example, it is having a functional group of NH4 plus ammonium ions, right? Now it is positively charged. Now if you add, say, some analyte A negative, so this analyte, it will go and it will bind over here. This anion, it will bind over here. Now you perform the elution. After you perform the elution, the column, your chromatographic column, it will only be having this anion. Now you can change the pH, you can change the ionic strength of your solvent, and while you are doing this ion exchange, these anions, they will be extracted out. Okay, they will be extracted out. Similarly, so if you see, this is a thing where we are having this anion is being what you call it, you are having this anion which is getting attached. Okay, so we can also have the cation also. Accordingly, we have this anion exchange and cation exchange chromatographic techniques. So cation exchange chromatographic technique is used when a molecule of interest is positively charged. Okay, and anion exchange chromatographic technique, it is used when the stationary phase is positively charged and negatively charged molecules are loaded to be attracted to it. So the example what I have given you, this is an example of the anion exchange chromatography. Okay, so later on, as I told you, by changing the pH or by running higher concentration of ions through the column, we can dislodge the anions or the cations. So these are the different types of anion exchanger systems. So these are the stationary phase molecules, DEAE cellulose. Okay, then the other thing, SP cephalose, which is a cation exchanger. Then what is the nature of these materials, and what functional group, which are what functional groups are there onto these stationary phases, they have been given. Now techniques by separation mechanism, size exclusion chromatography. I think I have already discussed about the size exclusion chromatography. This is just the schematic diagram which has been given. What happens? So these are different types of materials which are there, which are used for the size exclusion chromatography, and their corresponding molecular mass in daltons. So which grade is used for which type of molecular mass. Then types of adsorption chromatography, it can be categorized into thin layer chromatography, column chromatography, and gas solid chromatography. Then we can also have types of the different types of partition chromatography. It may be liquid chromatography and gas liquid chromatography. Affinity chromatography, it is just like this anion exchange. Over here we can have an analyte which is having a particular affinity for the stationary phase. Say for example, immunochromatography. So immunochromatography, what you have, say for example, you have the stationary phase. On the stationary phase you may you may functionalize the stationary phase with the antibody. Then you can have the antigen. So if this specific antigen is present in your analyte, they will go and bind, and the other analytes, they will be getting out. Then after that you can have a more strongly and what you call another standard or a sample which has got a strong affinity for the antibody. What it will do, it will replace the antigen of your test, which you can then collect and you can go for the quantification. So these are the different types of ligand and what are the target molecules which you can analyze over here. So with this we complete the chapter of chromatography.